Okay, so in this video we're going to look at the Smithsonian roof canopy by Foster+Partners. Familiar with this project from lecture. We looked at it a couple times, and what we're going to try to do is just replicate or approximate this effect, which is essentially making this complex curvature buildable by placing the flat panels into a certain kind of orientation that kind of produces this sort of sawtooth or this kind of tilting effect between the panels. Each one of these fits into their place, into the structure below, and it approximates the curvature while keeping the material fabrication affordable and doable. So we're going to model something similar to this. We're not going to model the exact geometry of the surface. We're just going to use a kind of a base surface that has similar properties, and we're going to try to panelize it in a similar way using the same logic. Okay, so the first thing is to go over and open up your Workshop 1 base file and just copy and paste the Smithsonian base geometry set. So this set of components here, you can just take that and hit Control-C and go to File, New, and just kind of paste that in there so that we're starting with a new file. Okay, now let's have a look at this geometry. So we can just take a peek by previewing it. So right-clicking on those components and previewing it. And I'm also going to go up to my my blue button up here and go to High Quality. So this is the base surface that I modeled. It's pretty quick. I didn't really spend a lot of time on thinking about what it looked like. I just wanted some double curvature and a kind of a valley and a peak, basically, right, to kind of try to approximate the same effect. So this is our design surface, right? This is the thing that we're going to rationalize into a paneled version. And the grid surface is something that sits just below. And we're going to use this to draw out basically our panel grid. And we're going to project it directly up in the Z direction to try to keep those panels as square as possible, right? If we subdivide this surface here, it has a more of a complex subdivision, and it'll give us parallelograms, or it'll give us panels that actually they won't have 90-degree angles on the interior angles. But we can try to get a little bit closer to that by projecting that a base grid up onto that surface, and at least in the top view it's going to appear a lot more rationalized. Of course, some of the panels will be a little bit different in terms of their area, and they may all be different in this case, but it's definitely a closer approximation. So I'm going to leave those on for a minute just while we get started before I turn off their previews. The first thing is to draw out a diagrid pattern that we want to project upward onto this surface. And for the sake, I guess, of clarity, I'm going to turn the preview off for the design surface and just focus in on the base surface for now, this kind of grid surface. I'm going to go to Lunchbox. It's one of the add-ons that you installed. Pretty standard these days, I would say. It's very useful to have this installed. It's got quite a few of good utilities. And I'm going to go to the Panels box here and grab the Diamond Panels component, which is the first one there. And I'm just going to go ahead and plug in my base surface into the input there. And as you can see by default, I've started to draw out what appears to be a diagrid pattern along our grid surface here. Now it's important to keep in mind that that's not just lines. That actually is, what that has created is a series of separate surfaces that are joined together basically at their edges. What I'm going to do now is increase the U and V value, right? So what this does is it increases the amount of subdivision we have, therefore, so basically by adding panels to it of a smaller size. So increasing the resolution. So I'm going to go to the Parameters tab, and I'm going to click on my panel here, and I'm going to add a couple of inputs. First one being 30. I can scale that down a bit. And then the second one, 15. And I'm going to move those a little closer, and I'm going to plug in the 30 into U and the 15 into V, which I think gives me a pretty good effect here in terms of keeping the panel square and the kind of, I think in actuality, of course, the case study building has more panels probably per area than this, but proportionally I think it's fine, especially just to kind of test the method. And again, this is a process that I think is pretty common. You sort of model out a kind of a test condition, see if your logic that you're applying to this condition will work, and if it does, you can start applying that to a geometry that's a little bit more in tune to the building form that you're actually designing for. But this is you can consider this a sketch, basically, of the paneling that we would apply to an actual design project. All right, so the thing that we want to do now is extract some of the information from this so that we can actually project it. We're not going to project the lines, we're just going to project points. And what we need to do is find that output, because right now we're only getting just we're getting, of course, just the panels, the surfaces. Okay, so the other thing, so what I'm going to do then is just go over into my surface tab up top, and I'm going to grab the explode component, also called deconstruct. In analysis, you'll find this little exploding cylinder here. It's called deconstruct brep. And what we can do is plug that in and find, and we're going to use the diamonds in this case. The triangles we can deal with in just a second, but they're separate outputs, so I want to deal with one at a time. And I'll just turn that original one off because we're basically redrawing them in a way. But we're also extracting now a series of things, right? So not only the surface face, but also the edges and the vertices. And the vertices is what we want. We're going to use those points to project upward to our design surface. Okay. All right. So the next thing then would be to go to back to the top part here and click on vector, the vector tab. And we're going to project point, right? So that's down a little bit toward the bottom on the left. Okay, so I'm going to grab that component, and what this is looking for is a series of points to project, which we know are these, and it's also looking for the direction in which to project them. We want, by default, this is being projected in the negative z direction. You can see it's 0, 0, negative 1. So we can fix that. We can just turn that around and just plug in a positive z vector there. So we're already in the vector tab. You can go all the way to the right here for in the vector box and find the unit z. And just plug that in there. And that doesn't need any kind of other input, it just needs a direction. We don't need to give it any kind of magnitude. The geometry to project onto, of course, is our design surface, and that's back over here. Okay, so you can go ahead and plug that in. And now what you'll see is a bunch of floating points that appear to be kind of, in a way approximating that surface curvature. And that makes sense because what we've done is we've projected them directly up to it. So where this point, for example, is projected directly up in the z direction, hits that surface, and then it's drawn right there. Now, if we look at this in plan, we'll notice that everything aligns, right? Because, again, we've projected it directly up in the z. So even though that these sets of points that I've just selected they're forming a curved surface in space, in the top view, they still appear to be rationalized into squares. Okay. So we've got to start at developing our paneling for our curved surface here. And what I'm going to start doing then is turning off some previews. We know we don't really need to see actually the design, the grid surface anymore. We just want to work now on our design surface. So the grid surface we can turn off, but if we go back and make changes to that, you'll see that, of course, the rest will update. Okay, so it's a dependency. So what's dependent on what? In this case, our design paneling is dependent on this base grid that's kind of somewhere down here, right? And we've kind of made it invisible. So that's what's related to what in this case. The next step now is to use these points to redraw a series of square or diamond-shaped panels. Okay, and now this is a grouping of points, which is now let's have a look at the data here. You'll see that the projected points are projected. They're organized into groups of 4, and that's because we projected them from separate surfaces. So had this not been a series of separate surfaces, we wouldn't have the right data. But because each one of these are separate, they have 4 points each, right? Any kind of square surface will have four outer points. Those points are organized into their own little packages. Those are being projected up, and that data is maintained. That's really good because we can take this data apart and redraw a set of new panels without having to think about the organization. It's really just kind of done for us. So let's go over to the Set tab. and grab this list item component. And plug that in there. And then zoom in on that component, you'll see a little plus sign emerge, right? So from a distance, these little these little secret doorways are kind of locked, but if you zoom in, they open up, and you can click on them to reveal a little bit more of the outputs, right? So in this case, we've got a bunch of data coming in. It's 202 lists. Each one of those lists have 4 items, so that means we have 202 panels, or potentially panels, and we have 4 points for each one of those panels. The index is going to refer to one of the points. So these are all the indices of all 4 points. It doesn't refer to the panel necessarily. It just refers to the points. By default, you're going to get the panel organization out of this because of the way that the data is kind of nested into one another, right? So if I look at the I output here, you're going to see 202 lists, 203 lists with 1 point being selected, and that's the same for all of these, but it's a different point. Okay, so it's one of the 4. We can use that to rebuild our surfaces, right? Because we can choose a 4-point surface component. So go over to Surface, Freeform, and 4 points, the first option, and just go ahead and connect right across. Okay, and you can see that it's now redrawing our panels for us, and it's doing so in such a way that creates a it starts to approximate the curvature by trying to create a flat panel. But of course, these panels are not 100% flat. It's just that they're created with straight line segments at their edges. But if you look a little bit more carefully at this one, you'll see that these edges, especially these 2 that are parallel, are not on the same plane, right? And that forms one of our problems, because what this is a twisted panel. If this were to be converted into glass, you'd have the wrong dimensions overall, because this is twisted in space, and that would be hard to fabricate. So what we want to do is make these truly flat by making all their edges parallel, right? The opposite edges parallel, and putting all the points in the same plane. And that's what we're going to do next. Okay. And what I want to do now is strip this data away. Before, like I said, we had the data kind of nested, right? But now that we've created a single item from 4 points, we can look at this and say, okay, well, this is now basically a single list of panels, right? So there's no reason to have that kind of data structure in it. It might actually get in the way for future steps. So what I'm going to do in this case, and this is not true for everything, but for this example, I'm going to need to flatten this, okay? And maybe we can get into that a little bit and through a question and answer if you want to kind of talk more about that. But to keep the video a reasonable length, I'm just going to keep going. The next thing we want to do now is to find the center point of these panels. And in so doing, we're going to try to find what's called the normal vector of this panel, right? Which is basically the perpendicular direction at the center point of each one of these surfaces. The reason why that's important is we're going to use that perpendicular direction, or that perpendicular vector, to set a plane in space that we can use to project all of our points to. By projecting all of these points to a single plane, we put them all on that same plane, and we can draw then a truly flat surface that has a very, very similar dimension. Okay, so let's go ahead and start. Also, for clarity, I'm going to start turning off some old previews and just kind of focusing in now on the next step, the next set of dependencies, which is now just starting with the surface. The first thing is to go to my Surface tab and head on into my area. Over in Analysis here, grab the area component. Okay, and this is going to give you a center point of that surface. But because these surfaces are a little bit twisted in space, that point may or may not actually exist on the surface itself. It could float off a little bit depending on the kind of three-dimensionality of it, right? And now, it's a good bet. It's a safe thing to do to try to force it to coincide, right? And we can do that in the next step. And also, we're going to need to do it anyway because we need more data. This is just a point, and we actually need, like I said before, we need to find the perpendicular direction. Okay, so we need to use the right components for this. So back in Surface again, there's a couple that you should grab, and one of them is the surface closest point. So here we're going to force those points to actually interact with those surfaces. And the other one you need, also in Analysis, is Evaluate Surface, which is down at the bottom left over here. Now I'm going to plug in my points, which is my C output, into the P input of this one here, which is the surface closest point. And I'm going to use these old surfaces here as the input for those. Now, I'm going to turn off this preview because they're going to look exactly the same. But the only reason, again, why I'm doing this is to first of all make sure that they're actually interacting. And then the other thing is that the output of this is exactly what I need for the next one. And this is the one that gives us my surface normal. All right, you can see that as an output here. All right, so these in conjunction with one another work well to get me the data that I needed. Okay, so the first thing I'll do is I'll pop these original surfaces into that component. And then I'll use my UV P values here, not the points themselves, but I need the U and V values, which are basically their kind of coordinates that exist along the geometry, not in the world, not in the kind of world Cartesian axes. So it's a little bit of a different data set. And now by plugging that in, you're going to find that things may look a little bit chaotic. And it depends on what settings you have on your preview plane size. In my case, I've got it at 2. I'll change that value, make it a little bit smaller, and you can see that now the plane is being drawn at a little bit more of a reasonable scale. You don't necessarily have to worry about this if it's looking a little bit crazy. Just go ahead and right-click and turn off that preview. We really don't need to see this anyway. We just need to know that we have the data. But if you did want to visualize these vectors, like I've been talking about, the normals, we can do that. We can get a test. We can at least test to see if they're in the right direction and if it's being drawn properly. So go to the Display tab up at the top and grab this little one over here in the vector box. It's the one at the top right called Vector Display with the orange and red arrows. And it's looking for an anchor point for each of the vectors, and we know that we have those points. Those are just the points on the surface. And then the vector itself is the n value, the n output. And you can see now what it's drawing is an arrow that's perpendicular to each one of those faces. Basically, it's revealing the direction of that vector for us. Now again, depending on the units in your file, you may be seeing a slightly different representation here of these arrows. You may have to zoom in. They might be very long or they might be kind of short. It really depends. And if so, you can always change the magnitude of that vector. But in this example, it looks pretty good. So we know that they're going, first of all, in the right direction. They're facing upward. And they're all, they appear to be perfectly perpendicular to each one of those faces. So we have the data. Everything worked in the way that's expected. I'm going to turn off that preview and just keep it there in case I need it later. Okay. Now, before we start adding a plane that we're going to project to, we need to draw the geometry that we want to project. And we have it more or less here, except we want an offset, right? The panels themselves don't touch. They actually hit a structure. Well, I mean, that may not be true. It looks like they get really close, but there is a little bit of an offset between them, you know, for weatherproofing and so on. And for the sake of this exercise, I guess it doesn't really matter if they touch, but just for the sake of this exercise, I'm going to assume that there's a space in between. We're going to do a little bit of offsetting to kind of allow the structure itself to kind of appear, or to give it some breathing room, actually. For the next step later, and maybe in a different tutorial, would be to kind of add the waffle grid structure beneath this thing. So we're going to do a little bit of an offsetting. And to do that, I'm going to head over to my Transform tab and grab, in the affine box, I'm going to grab the Scale component. Okay. Actually, I've just realized that I've been doing this tutorial using icons. I could, if it's easier, switch over to the names. Maybe I'll do that from here on out. Okay, so what we're trying to scale is the panels, right? So we're going to try to scale these. Okay, I'm going to turn those off now just for a second because once we fix the rest of these inputs, this won't happen, and we're going to want to see our result a little bit more clearly. Now what we need to do is give this the appropriate center point. Right now we're giving it the wrong center point. It's the world axes, which is why the whole thing is being scaled toward the center of the screen. The center of scaling is going to be each one of our panel points, right? And we can use either this one or that one. You can use that one as well. It doesn't really make any difference. They're basically the same point, so I guess I'll just use this one. And now we just need to give it a factor of scaling, okay? And that's a number between 0 and 1. A factor of 1 is essentially 100%, right? So it's a scaling of 0. A factor of 0 is, of course, going to throw an error because you've scaled it to nothing. Anything in between, 0.5 of course is exactly half the size. So anything in between is going to be a kind of a factor of its original size. And I'm just going to put a small offset in there, you know, kind of like what we see in the building. And then I'm going to keep going. So I'm going to change that to, I don't know, 0.95. And I think that looks good enough for now, again, as a kind of sketch. Okay. I'm going to turn off this center point. We actually don't really need that anymore, unless you want to see it. It's up to you. And then now, what we're going to try to do now, again, like I said before, is to straighten all these panels out. Right? We know that they've got some twists in there, just based on the geometry. There's no way that these can all be flat. You can kind of really see it at the edge there. Looks like a kind of approaching to be a Pringle shape there or something. So we want to be able to fix that, and we're going to project it to a plane. So let's look at what kind of component that's going to be. That's we can go to our vector tab. Let me make sure I got that right before I say anything else. Might actually be in Translate. Yeah, sorry. In the Transform tab, you'll find the projection tools, and down at the bottom here you'll see Project onto a plane. There's Project along a plane and direction. You can experiment with that later maybe. We're just going to choose the first one for now because I think this works just fine for this experiment. So Project is our tool, and we're going to kind of see what it needs. Okay, so it needs, first of all, geometry. We know what we've got that, or we almost have that, and we need a projection plane. Now the world XY is not what we want, of course. We want a plane that's perpendicular to those vectors, like that we found before. That's what the point of all this was. So before we start plugging anything in, let's see if we've got the right kind of data structure. It looks like we do. We have no, as a matter of fact, we do not have the right data structure, and I'll explain that as we go here, because this is a single list of items. The last thing we need, though, is to project a geometry, and by habit, and maybe by, I think, good practice, instead of projecting the panel itself, this surface, to that plane, which may or may not work, I haven't tested that, I'm going to just project the points, right? So we have to go back, to do that, we'll have to just explode that surface again. So I'm going to go to the Surface tab, grab this Deconstruct BRep again, like what we did before, and I'm going to find those vertices again. Now the data set here is like it was before, right? This is a different type of data. It's a grouping of 4 points, right? So I have more points than I'm going to have frames, and that's okay so long as the data on the left side, the number of lists I have, matches the number of frames, right? So you can see that if you hover over it, says 203 frames. Here I've got, it says 812 values, but I have 203 lists. So each one of those lists will be compared to a frame. So each one of those sets of 4 points will be projected onto only one frame. That's important, but in order to get that right, you have to match the data structure, right? So if I just kind of show you this for a second, you can see that this structure is broken down into a series of separate lists. This data structure is one single list. This is going to be a problem if I plug those two in to compare them, because I'll end up with an exponentially more data than I need and potentially a computer crash. How do I fix it? In this case, it's very simple. You can right-click on that output of F and just click the graphed option, okay? And that's going to produce the same data structure. So it's going to put each one of those frames on its own kind of separated list. Even if it's just one item, it's okay, because now our zero index here will be compared to our zero index here. Okay, so let's plug our frames in, and let's plug our geometry in. Now you're not going to see anything really happen there, right? This is a very subtle movement, and if I zoom in to one of these intersections here, hopefully we'll get a better sense of it. Yes. You can see now that there's a series of points that are hovering over where they originally were. That means they've been moved to the plane that's been drawn out here. Okay, so if I turn that back on a minute, right? This plane that's being represented by this grid is a flat plane perpendicular to that center point. All those points that are now selected in green, because I have that project selected, those are now on the same exact plane, which means they are flat. Okay. You can, again, zooming in on that will reveal what happened. Now I'm going to turn that preview off again, because the last step, and you might be starting to get the picture here, is to just simply rebuild our surfaces through this new set of points. And the way that we did that over here was like this, right? We listed them all out first, and then we just redrew them. So we can actually copy and paste this if you want, or you can rebuild it. It's just a list item in a surface 4 point. I'm just going to copy and paste it, plug in a new input, and then turn on my previews. Okay. And now we have a series of surfaces that are flat. Very, very similar in effect to the Smithsonian canopy. And if I go to the area that has a little bit more curvature to it in our base surface, you can really see how it's working, right? So if you look down the line here, you'll see that they're all rotated again away from one another relative to their perpendicular directions in space. Not all that dissimilar, I guess, from this, right? So if I look at those two things together, you can see we're actually getting pretty close to having that effect working for us. Okay. And that's more or less it for this exercise. This is just an exercise in subdividing surfaces, extracting data from those surfaces, and especially the introducing of the normal direction, which is a pretty common process in order to do, in order to add, I guess, geometry to complex surfaces. And this sort of wraps up this exercise, at least. Anyone interested in drawing out the structure, let us know, and we can kind of add a part 2 to this.